Hi, and welcome to this video on differentiation from year 2 of the course. And what we're doing is looking at the second differential, which you might be thinking, well, we did that in year 1, it was max and min, and you absolutely did. But what we're going to do is extend the principles we looked at then to start looking at whether a curve is concave or convex. Then using second differentials to help us locate points of inflection, we'll have to discuss what a point of inflection is. And then there's a twist in the tail at the end, which, let's say, we will get to. It's something that you need to watch out for. And that's that third point there. Okay, right, here we go. Let's just quickly recap what we did in year 1. I'm going to whip through this fairly swiftly. So there we've got a cubic, and we've got a minimum point at x equals minus 2. So we've got our curve doing that. And we know that when x is less than negative 2 dy dx, the gradient is negative. At x equals minus 2, it's 0. And above x equals minus 2, it's positive. So what we've got is the gradient of the curve there goes from negative through 0 to positive. So the gradient of the curve is increasing as we go around that minimum point. And if we have a look at what's happening at the maximum, same principles. We've got the curve increasing, being 0, and then decreasing. So it's starting with positive, going through 0 and becoming negative. So what we're saying there, the gradient of the curve is decreasing as we go around that maximum point. And so that's what's going on. And we know from that that we've got the second derivative, which measures how the gradient is changing. So if we're saying that the gradient is increasing, then we've got d squared y over dx squared is greater than 0. So we've got a minimum. And if the gradient is decreasing, then we've got a maximum, and d squared y over dx squared will be less than 0. And that's all the stuff that we talked about in year 1. And now we've got this other thing here, so this point of inflection, which is d squared y over dx squared is equal to 0, and that's the bit that we're going to be focusing on a little bit later on, and we'll come back to that one. Now, if we're talking about convex or concave curves, what we're saying is that if the gradient is increasing, the curve is convex. And let's just have a look at that. So there's a curve that's starting off with a negative gradient, and you can see it's going from negative through 0, there's a minimum there, and it's getting steeper and steeper, so the curve is what we say convex, which is that one there. And the alternative to that is concave, where we've got something like that, where the bend is going the other way, and what we've got here is an increasing gradient, a positive gradient that becomes a negative gradient. So what we've got is, if we've got the gradient increasing, the curve is convex, and if we've got the gradient is decreasing, then the curve is concave. And to remember which way around those two things are, I just link that to kind of your d squared y over dx squared greater than 0 is a minimum, that's your convex. D squared y dx squared less than 0, that's a maximum point, and so that's your concave. Right, now that's what I've just said there. So there's your convex, there's your concave, and so essentially it is basically exactly what we've had previously in year 1, but now rather than just calling them max and min, we're describing them as convex and concave. On we go. Let's just have a little think about what's going on with this cubic here. So I've got a cubic curve, and if I'm just going to add onto my graph the first derivative, so differentiate it, I get 6 minus 3x squared minus 6 minus 3x squared, so that's this thing here. And we can see we've got our stationary points on our curve, where the gradient of the curve is 0 at this point here, when x is minus 2. And you can see that's indicated as my derivative having a value of 0. That's that bit there. And the same thing's happening over here. At any point it might be you want to just stop the video and have a little think about what's going on, because it is going to get a little bit complex in places. There's my second derivative, so I've differentiated again. So differentiate this thing here, I'm going to get minus 3 minus 6x. And so that is the second derivative. It's indicated by the purple line. And if you have a look at what's going on here at x equals minus a half, this is where my derivative stops being, second derivative stops being positive. So when it was positive, we were talking about a convex curve, and it becomes negative when we're talking about a concave curve. And so up until this point at x equals half, we can see the gradient is increasing because the purple curve is above the x-axis, and beyond x equals half, the gradient is now decreasing because the values are below the x-axis. And what we've got is this point here, and if we relate this back to the original red curve, what you've got is it is convex there, and at this point here it stops being convex and starts being concave. So we've got this change from convex to concave which occurs right here where my cursor is at x equals minus a half. And that's the point when d squared y over dx squared equals 0. You can see it there. And that's the thing that's referred to as our point of inflection. So technically what we've got, a point of inflection is defined as being the point on the curve where it stops being concave, sorry, stops going from convex, becomes concave, or vice versa, the other way around, where it changes from one to the other. And it's another way of saying that, it's the point where the sign of d squared y over dx squared changes, so therefore it's got to occur when d squared y over dx squared is 0. So let's have a look at an example. So I've got a cubic curve here, and we're being asked to prove the curve is convex on the interval 3, 5. Now, just be clear, this thing here is not a coordinate. This is a range of values. When we use square brackets, it's a range of values. This is the values going from 3 to 5. So we've got to prove that the curve is convex on that interval there. Right, here we go. So let's differentiate it to begin with. We get that. Let's do the second derivative. So differentiate that. That's going to become 6x minus 6. And if we're going to prove that the curve is convex, we've got to prove that d squared y over dx squared is greater than 0. And so if we just set our expression for d squared y over dx squared to be greater than 0, we can see from solving this that the curve is going to be convex for any values of x greater than 1. So therefore, if we've got an interval going from 3 to 5, we're in that range. So therefore, we've proved that the curve is convex over this particular interval. So to find the points, the coordinates of inflection, the point of inflection. Well, the point of inflection is going to occur at x equals 1, because imagine if it occurs when d squared y over dx squared equals 0, so just imagine doing this, but replacing the greater than sign with the equal sign, and so there you go, we've got the point of inflection is when x equals 1. It says find the coordinates, so the last thing to do is just to put that back in to the equation, and that's clearly happening at the coordinate 1, 0. So there we go. Final thing to look at. We have said that a point of inflection occurs when d squared y over dx squared equals 0, and that is absolutely true. But let's just have a look at this curve here. So we've got y equals x to the power 4. So if I differentiate that, first differential 4x cubed, second differential 12x squared. We've got a point of inflection, apparently where d squared y over dx squared equals 0. So if we say, well, when does that happen? Let's put 0 equal to 12x squared. That gives us x equals 0. But we can see at that point there that at x equals 0, our theory tells us we've got a point of inflection, but there is no point of inflection there. This curve is entirely convex all the way around. It's not going from convex to concave. It's not changing. So it's clearly not a point of inflection at x equals 0. So we've got to be a bit careful, because we're saying that d squared y over dx squared equals 0 is a necessary condition, but it's not on its own sufficient to prove we've got a point of inflection. To prove we've got a point of inflection, we've got to show a change from convex to concave. So what you would have to do is say, well, in this case, what I'd be doing is say, well, can at x equals 0, we think we might have a point of inflection. I'd go to the left of that, maybe go to x equals minus 0.1, and look at the sign of d squared y over dx squared there, go to x equals 0.1, do the same thing, and show that we haven't got a change of sign of d squared y over dx squared, so we haven't got a point of inflection. And the converse of that, of course, is that if we did get a change of sign either side of where d squared y over dx squared equals 0, then we have done enough work. That is just, like I say, I'm putting it there, it's just one to watch out for. It might pop up on your exam.